In this problem, the word elastic collision has been used, and so let us take some time to first understand what exactly is an elastic collision. Although this topic will be dealt with in detail at a later stage, we really need to know only one type of elastic collision for the purpose of solving this problem, and that is an elastic collision between two equal masses. So the idea is the following: when two objects of the same mass they collide, let one of the masses be drawn here, that's m. The second object is over here and its mass is also m. Now let's imagine that this mass is moving in this direction with a velocity v1, and this mass is moving in this direction with a velocity v2. Now assuming that the collision is perfectly elastic, and also assuming that it's not a glancing collision but it's a head-on collision. A glancing collision would be a collision which occurs between the striker and the piece of a carom game. It's called a cut in a carom game. So typically what would happen is the striker moves in this direction, and if the piece is over here, that would be a head-on collision, and if the piece is actually over here, that would be a cut in carom, or it would be called a glancing collision in physics. So currently we are talking only about head-on collisions, which is the type of collision which is mentioned in the problem. So what happens in such a collision, elastic collision, head-on collision between two equal masses, is that the velocities of the two colliding objects, they get interchanged. Now what this would mean is, after the collision is over, the left hand side mass will be moving with the velocity of the right hand side mass, in other words v2 towards the left, and on the other hand the mass which was on the right hand side, it would be moving with the other mass's velocity, in other words it would be moving with a velocity v1 towards the right. And that is the only point that you should currently remember regarding collisions for the purpose of solving this particular problem. Of course we will be doing collisions in detail at a later stage, in which we will discuss collisions which are not elastic, in which we will discuss other types of collisions, but currently this knowledge is sufficient. So let me now describe the conditions given in the problem. Over here in the center there are two concave mirrors connected to a stand, and the mass of this entire object is given to be m. Similarly, the mass of these two blocks on either side of the mirror stand system, each of these blocks has the same mass m as the mirror stand system. The radius of curvature of each of these concave mirrors is given to be r. Note that r is not the directed radius of curvature. So r is a length, it has to be positive, and as you know, for a concave mirror, under the usual Cartesian convention, the directed radius of curvature would be negative. So whenever we are using the directed radius of curvature, for example in the mirror equation, 1 upon v plus 1 upon u is equal to 2 upon directed radius of curvature, so we would be using minus r instead of r. Similarly, the directed focal length, which appears on the right hand side of this equation, in place of this I usually write 1 upon f, which is right, but f in this case is not r by 2, it's going to be minus r by 2. Now the mirror stand system is given to be stationary, while each of these blocks has its own velocity. That is, the right hand side block, which is called B, is moving towards the left with a velocity v, while the left hand side block A, currently it is stationary. Of course, each block, including the left hand side block, is free to move on the floor, which is assumed to be frictionless. The mirror stand system is also free to slide on the frictionless floor. Now the data given in the problem suggests that this black line which I have drawn over here is to be treated as the x-axis, as a number line, and the positive direction of the axis, the number line, is towards the right, and so I can write down the coordinates of certain points. For example, this point over here, the center of the mirror stand system, that is to be treated as the 0 of the x-axis, and since this distance between B and the mirrors is given to be 2r, obviously this coordinate would be 2r. This is the x-axis, of course, and likewise this distance between the stationary mass m and the mirror system is also 2r, but it's on the negative side of the origin, so this point has a coordinate of minus 2r. I think that now we are in a position to start the part A. In part A, it has been mentioned that if we assume this particular diagram to be drawn at t equal to 0, then we have to find the positions of the images of the two blocks formed in their two respective mirrors at t equal to r divided by v. So that's the new time. You can note that the time interval which elapses is t equal to r by v itself, because the starting time is assumed to be t equal to 0. So of course we'll have to draw the new picture in which the objects are shown at this particular time. Now clearly, in this time interval, the displacement of block B is going to be its velocity multiplied by the time interval, which is r divided by v. In other words, it's r. So this means that block B will move a distance r towards the left, and it would arrive somewhere around here. So its new coordinate would of course be r in place of 2r. So I'll be showing this block B to be in this position over here at an x coordinate r, and now we actually do the calculations. We find out where are the respective images. So let's consider block A first, and so let's apply the mirror equation to find the image of object A. Of course, the mirror equation is 1 upon v plus 1 upon u is equal to 1 upon f, and we have to find v, the coordinate of the image. So I'll write 1 upon v over here plus 1 upon u is the coordinate of the object, and the object is A. The pole of this mirror is of course the origin, and with respect to the pole or the origin, the object's coordinate is minus 2r. So u is of course minus 2r, and that's equal to 1 upon f. Now what is f actually? We'll have to locate where is the focus, and we are talking about the left mirror. Of course, the left mirror is the one which produces the image of object A. Now the center of curvature of this mirror, let's say it's somewhere over here, and we know that this distance is equal to r, the radius of curvature. So that's the center of curvature, and The midpoint of this particular line segment from the pole to C is of course the focus of the mirror F. So clearly the focus of the mirror has a coordinate which is equal to minus r divided by 2, which is going to be substituted over here. And of course for F I'll write minus r divided by 2. Now when you solve this equation for V, you get an answer of V equals minus 2r upon 3. So this means that the x coordinate of the image of A is equal to minus 2r divided by 3. Now let's try to find where the image of B is. If you look at the figure, you realize that B, which is at a coordinate of r, is at the center of curvature of this particular mirror, and hence you need not actually apply the mirror equation. It's a very easy case to analyze. When the object is at the center of curvature, the image must also be at the center of curvature, which essentially means that the image of B will have an x coordinate of plus r, and that's the answer of part A. Now we can turn our attention to part B. Remember this diagram which we have drawn, that corresponds to the time equal to r divided by V, and in part B we want to find out what happens at t equals 3r upon V. We will do that, but before that there is a very important intermediate time between these two times, and we have to find out what happens around that time, and that time is t equals 2r divided by V. Now at this time what will happen is the block B will move. Remember this picture is at t equals r by V, and at t equals 2r by V a time interval of another r by V has elapsed since this picture was taken, and so block B will move by V times delta t, which is V into r upon V, towards the left, and it means that B moves by a further distance r towards the left. Now clearly in the picture it would mean that block B is somewhere over here. Neglecting the width of the mirror stand system, it means that basically B will collide with the mirrors, and at this time, that is at t equals 2r by V, there is going to be a collision between block B and the mirror system. Remember the problem mentions that the collision is elastic, and so what that means is that B, which was moving with a velocity V, it imparts its entire velocity V to the mirror stand system, and before the collision, of course, the mirror system was at rest. So what that would mean is that block B after the collision comes to rest. Of course, the reason for this we have discussed earlier. The reason is in a perfectly elastic collision between two bodies of equal masses. If the collision is head-on as described or as is shown in the picture, the two masses will simply exchange their velocities. And then of course we have to analyze what happens at time equal to 3r by V. So there is a further time interval delta t in between this time and this time, and delta t is r by V. In this additional time interval, nothing is going to happen to block B. block B is going to remain at rest. But something is going to happen to the mirror stand system because it's moving with a leftward velocity of v. So obviously the mirrors will move by a distance of r by v, that's the time interval, multiplied by the velocity is v. This time it is the mirror stand system. It moves by a distance r towards the left, and the picture therefore at t equal to 3r by v will be as follows. So at t equal to 3r upon v, the mirror stand system will have moved leftwards by a distance of r. So that would mean that it would be located about here, and the coordinate of this point is of course equal to r. So let's move it over there like that. This is the new location. Remember, it's still traveling leftwards with a uniform velocity of v, and in the meantime this block B has stopped at the origin. So I'll move it there like that. And in this situation we now have to locate the images of A and B in their respective mirrors. So that's quite easy. If you look at A, its image is going to be formed in this mirror, and we realize that since this distance is equal to r, quite clearly A is located at the center of curvature of this mirror, and so the location of the image of A will be at the same coordinate, that is at x is equal to minus 2r. So image of A, the x coordinate is minus 2r. Likewise, if you look at the object B, the distance between object B and its corresponding mirror is once again r. Quite clearly B is placed at the center of curvature of this mirror, and so the image of B will be formed at the same point, that is at x is equal to 0. X equal to 0, and that would be the answer of part B. Now we can actually go to part C, in which we are supposed to find what happens at t equal to 5r divided by v. And once again, in between t equal to 3r by v, for which this picture is drawn, and 5r by v, there is an important time, namely t equals 4r upon v, in which something important is going to happen in between these two times. And quite clearly at this time what is going to happen is a collision between the mirror stand system and A, and once again, for the same reasons as described previously, the velocities of A and the mirror stand system would be interchanged, which means that at t equal to 4r by v, the mirror stand system would be somewhere over here like that, and after the collision is over, the mirror stand system would then become stationary because A was stationary before the collision, and likewise after the collision A, instead of remaining stationary, would acquire the velocity of the mirror stand system, namely v, towards the left. And that is the situation that has been shown in this figure. It is the situation just after the collision which occurred at t equal to 4r upon v. The block A is moving to the left with a velocity v. The mirrors have become stationary. Now what happens at t equal to 5r by v is that a time interval of delta t is equal to r by v will have elapsed since this particular picture was taken, and so although the mirror system remains permanently at rest, the block A will have moved in this given time interval left by a further distance of its velocity is v multiplied by delta t, that's r by v. So A will now have moved left. It will no longer be at the coordinate minus 2r, but it will be at the coordinate minus 3r, which is somewhere over here. So that's x is equal to minus 3r. So I'll move block A over there like that, and of course A continues to move towards the left with the velocity v. The time, of course, t is 5r upon v. The mirror system is stationary at x is equal to minus 2r. Now you may be worried that the collision between the mirrors and block A took place at this point, and we had called this point x is equal to minus 2r, but we need not worry because we are assuming here that the breadth of the mirror system is quite small, so you could as well call this point minus 2r. X is equal to minus 2r, it doesn't matter. And so we once again have to find the locations of the two images. So as usual, we start with A. A is in front of the left hand side mirror, and this distance is equal to r, the radius of curvature. So obviously A is at the center of curvature of this mirror, and therefore its image must be at the same location, that is x is equal to minus 3r, which would then mean that the x coordinate of the image of A would be equal to minus 3r. Now we can apply the mirror equation to find the image of P. You can see that this distance is equal to 2r, and I'll just apply the mirror equation. 1 upon v plus 1 upon u is equal to 1 upon f, and hence 1 upon v plus 1 upon, now to find u, remember, according to a Cartesian convention, the direction towards the mirror is taken as positive, and so the coordinate of the object P with respect to the pole of the mirror is equal to this distance 2r, but with a negative sign. So I write minus 2r, and that's equal to 1 upon, once again the directed focal length of this mirror is going to be minus r divided by 2. Usually, of course, we write f is equal to r by 2, but there r is the directed radius of curvature, and here it's the actual radius of curvature, so we have to introduce the minus sign. And when I solve this equation, I get v equals minus 2r divided by 3. But remember, this v is the coordinate of the image of P with respect to the pole of the mirror. So in other words, this point. So what it means is, if I treat this point as the origin and I draw a number line passing through the pole, then of course the image location is at minus 2r divided by 3 over here, minus 2r divided by 3. But we really have to find the coordinate of the image with respect to this origin. So what I can do is, I can merely take this point minus 2r, and I just add, knowing that this distance is 2r by 3, I just add 2r by 3 to this coordinate. So the x coordinate of P's image would be minus 2r plus 2r by 3, and of course that would be minus 4r divided by 3. So that would be the answer for the x coordinates of the images of A and B.